Greetings, computer hobbyists. Welcome to a special video presentation hosted by Hey everyone, welcome back to my YouTube channel. It is July. 3 years ago this month, I did my first video sitting in this chair, and I attempted to do a power supply special for a now defunct tech website. The website didn't work out, but I got the taste for it, and so now here I am 3 years later still making videos, and I thought, why not do a throwback by going back to power supplies again? There's a bunch of 0 to 30 volt power supplies as well as power supply modules on eBay, and I decided to pick up a couple, take a look, and see, hey, what can we do with these? And I found enough there to make a complete DIY power supply and document it. So, is it worth the money? Probably not. There's just too many cheaper ways to do this, but if you enjoy putting your hands to work doing something fun, you'll like this. Jump on in with us. The water's warm, possibly because it's electrified. 3 years for this channel is kind of impressive, and what kicked it off was a power supply. This power supply, in fact, along with a couple others that were featured, but this one's the one I've kept and continue to use to this day. 12 volt CC, maximum of 4 amp output. Somewhere in time I also acquired this. This is a Hewlett-Packard E3631A. It outputs 0 to 6 volt, 5 amp maximum, and plus or minus 25 volts at maximum of 1 amp. This is an old but very good instrumentation grade power supply by Hewlett-Packard, later Agilent, now Keysight Technologies, and whatever they spin off next. It is, however, a little bit big and cumbersome to get in and out. You have seen this in a number of my videos, but most of the time I'm not using the symmetrical supply, and I may want more than 1 amp. So I had a thought, we're coming up on 3 years, why not go back to the roots and do a power supply project that's a little bit smaller and more generally useful. These recently began to appear on eBay. This is a little tiny buck boost power supply module. We'll take a look at it under the microscope in a minute. But it has a little rotary encoder that supposedly can do 0 to 30 volts, and I don't know what else. These are about 16, 17 bucks right now. That may change in the future, but that's a really good price for what this module is capable of. However, this module requires some kind of DC input. Looking at the box here, it says V in 5 to 30 volts, V out 0.5 to 30 volts, I out 0 to 4.0 amps. Now this little device looks like it's everything you need, right? Maybe put a transformer behind it. How hard can it be? Well, that depends on how complicated you want to get. I got some parts and pieces, but what I want to do is in this chassis. And if you look at this chassis and you look at this module, you're going to be like, what on earth are you thinking? You can buy variations of this chassis at a much smaller size than this. Well, I'm going to do a transformer-based power supply. I'm going to make sure I can get the full 4 amps out of this if I want to, and so that's going to require some additional considerations. But even so, once this is all together, this here is a much more smaller, more manageable box to move around than that giant HP power supply, as much as I love that. And it will also be a little bit more flexible than that 12 volt supply. Come with me over here to the workbench, and let's take a look. Okay, before doing anything drastic with this module, let's go ahead and check and make sure it works. First of all, we've got our classic 13.8-ish volt power supply here, and I've got wiring connected to the input and output on here. Note very carefully, red positive to red positive, V in positive, black V in minus. I just want to make sure that I've got my polarity correct coming in, because I have no idea if this is protected against reverse polarity or not. For now, let's just experiment with this automotive light bulb. So, turn this on. One very quick boot. Currently the default voltage has been set to 12 volts, but ideally should just be able to. And I'm getting about 1.97 amps out, just under 2. And with the low beam on this same bulb, 540 milliamps. So that works pretty nice. This knob here, you can press it to actually turn the output on and off. Interestingly, the voltmeter actually reads the decay on the output. So let's go ahead and connect this again. I've now got both filaments on for 2.5 amps. Off, on. So it cycles pretty gracefully, doesn't seem to have any issues supporting the load. This same knob, if you just want to do some fine adjustments without going into the settings, you can start turning it and the output voltage starts changing. So once again, let's just connect this, get our 2.5 amps going. As I turn the voltage down, I should also see the current drop, and the bulb will gradually get dimmer. That seems to be happening, and it's Very graceful. It is correctly slewing the voltage down into the load. No issues. I can also turn it off. Done. So that's the basic operation right there. And it also seems to have a memory. I last left it at 11.16. Turn that off for a moment. Turn it back on, and yeah, it's back at 11.16. What's worth keeping in mind though, because it will default to the last voltage it was set out, and it will default to power on. So if you were last using it for, say, 20, 25 volts, and then you come connect a 6-volt load and just flip it on without thinking, you're gonna blow it up. Now let's look what happens if we press buttons. I already showed you that if you press this one, turn the output on and off. If you start rotating the dial, you just start adjusting the voltage. Let's press this. Okay, I've now just switched the bottom display from amps to watts. So now I'm looking at it in terms of 30 watts instead of 2.5 amps. Press this again. Now it goes to amp hours. So that's a combination of how much current I've drawn for however long time this has been on since it was last turned on. And now if I do that, we can watch it start cycling up. So that gives me some rudimentary power metering. Press this again. Now it's how long I've been on, just over a minute at the moment. One more time, back to amps. Press and hold this display. Now I'm looking at the A voltage on the input side. And I was hoping that when I did that, I would also be looking at the input current so I could compare input to output. But after playing with it for a bit, I don't think that's what it's doing. This is only the output current, output power as far as I can tell. Now let's go into the UI menu and see what we can do for better adjustments. Okay, I've now opened the settings. Limit upper, you're saying my voltage that I'm setting must be higher than this value, or I don't want to try and attempt an operation. So this is a protection on the low side if for some reason you don't want to try and start a load that would otherwise be below its voltage startup limit. There are situations where that can be useful. Motors, for example. Output upper, same thing. I don't want my voltage to be above a certain limit or I won't start up. So for example, if I never want to go above 20 volts, I could set that. But notice how that last digit is flashing. If I press this, I start to cycle through them. So now I can scale at the tenths rather than the hundredths, or I can scale at the 1 volt level, or I can go all the way up here. This is the output current limit. So right now the absolute maximum limit is 4.1 amps. But in order to examine what this does, let's set it at 2.1 amps. Actually, let's set it at 2.2 just to make sure I have some margin. I can also do the same thing, except I can set the limit in watts instead of amps. This here, if I press and hold that, I can now actually set a limit. In this case, the maximum is 60 amp hours, and then stop the unit. Same thing, except now I can do a timer to shut down. Finally, I can set a temperature threshold to shut down. Currently it's at 80°. That is the lowest setting. You can actually go higher. I'm not sure why you would want to, because I've got, that's way too hot for this thing to be getting. And finally, you can calibrate. Now, I don't think I need to, because I know this thing here from other meters I've connected to it. They all say that it outputs around 13.6 volts or so. So I think that's pretty accurate. Calibrate the output, calibrate the current settings. But in any case, now back to the main menu, and I'm going to exit. And you can also press and hold UI any time to just exit this calibration menu. If I press and hold this again, however, there's a read on my current temperature of the heatsink back here. According to this, our heatsink's running at 30°C, so let's just connect this light on for a second and see if we can watch that rise. Sure enough, pretty quickly too. Yeah, I can feel it warming up. And finally back to the output voltage. So here's what I'm going to do. I'm going to turn it on. I'm going to leave that output current limit at 2.2. And now we're back to normal operation. Remember, if I turn on both of these, I should be around 2.5 amps. Let's see what happens. Lets it go for a couple seconds and then shuts down. I've actually exceeded the current limit that I set. And I should get the exact same result if I just turn it back on with both filaments connected. Bam. I have no idea what that CC does. I was hoping maybe that was a current clamp setting, that when you set your upper current limit, that instead of just shutting down, it would actually clamp at the maximum current and that would be it. I don't know. Don't have a manual for it, but the rest of it, pretty straightforward to use once you realize the interaction between these three buttons and the menus. And I think this will be a good power supply module. All right, let's kick this off with some basic math. Here's our power supply module. 0 to 30 volts at a maximum of 4 amps. Backside, we've got 4 terminal points. We've got plus or minus DC in, plus or minus DC out, and a heatsink, which I suspect is going to need a fan in order to give a full output. But let's do a little basic math to plan our power supply. Very first of all, we know what the maximum output is. we have 4 amps at 30 volts. If we do the math on that, we need 120 volt amperes. But actually we need more than that, because this is not going to be a perfectly efficient power supply. Switching supplies like this are way more efficient than old-fashioned linear regulators. It might be as high as, let's say, 95%, 0.95. Just to be on the safe side, let's divide 120 VA by 0.9 or 90% and see how much power needs to come in order to get that power out. So we're actually going to need 133 volt amperes on the input. Now here's how this is going to be laid out more or less. We are going to have AC input, which since we're in the US is going to be mains. We're going to have line and neutral at 120 volts AC, and then we need some sort of power supply that outputs DC at, who knows, we need to figure that out. It's then going to come into this module, which we'll sketch up like this with a pair of nifty little buttons right there and a big old rotary encoder dial right there. And then coming out of here, we're going to need some kind of connection point in order to access it, and we will get plus or minus 0.5 to 30 volts DC at a maximum of 4.0 amps. Looks simple. Here's the problem. This power supply unit needs to output 133 VA roughly here. Doesn't matter what voltage we pick, we need to have a corresponding current that gives us 133 VA. First thing you might look at is, well, you can get lots of, like, say, 5 or 12 volt power supplies out there. I mean, that's easy to do, but let's take 133 VA and divide it by 5. 27 amps. That's a lot of current for a small project like this in order to get 0 to 30 volts at a maximum of 4 amps out here. I can now input as little as 5 volts here, but if I really want to input 133 VA, that's just not practical. So my next common supply size is 12 volts. 133 VA and divide it by 12 volt. Well, 12 is a little bit more than twice than 5, so I'm going to expect that to be a little bit less than half of 27, but let's get the exact number. 11 amps, more or less. That's a little bit more approachable, but it's still a bit much. And what you're seeing here is that if I want the maximum output of 30 volts, I should probably be putting in a DC voltage that's a little bit closer to the 30 volts I want. Well, another standard size is 24 volts. Let's take 24 volts. Now I get a maximum input of 5.5 amps. That's looking a little bit more feasible. But another option, if you want to make sure you're getting something high quality, is to buy a laptop charger, a used laptop charger, from a known company like Sony or Dell or whoever, and those typically operate somewhere around 19 volts. That's within reason. That's also a part you can get fairly easily from surplus or the used market without paying a small fortune. Laptop power supplies are usually self-protected, so you're not too concerned about starting a fire over here because something didn't cut off when it should have. So this is a very viable project if you want to do it very basic. Now, of course, I never do things that way. I always make them overly and unnecessarily complicated. So I'm going to show you another way to do this today, where everything goes in a nice project case, plugs straight into 120 volts on the backside, and then outputs to a nice pair of banana plugs on here. Depending what your setting is on this, you're not going to be drawing full power at all times, but if you want to be able to draw full power, you're going to have to plan for that. This here's a big box of parts. For your DC power supply, you got a couple options. This here is one of them. This one outputs only 24 volts at 0.7 amps or 700 milliamps. That's not a lot of VA for what we want to do. That doesn't mean you're stuck with just this. There are different variations of switching power supplies out there that can output more than this. The other way is to use found objects. This transformer here came out of an older uninterruptible power supply. I think it was like Trip Light or one of those other brands. But nonetheless, it did happen to have a pretty hefty transformer in it. You won't find these in most newer uninterruptible power supplies, from what I can tell. They pretty much have all switched over to switching power supplies like this, only much bigger. What this one does do for us is here on black, white, brown, we have our input. Depending on where we want to tap it, we can either go 120 volt 0 on black and white, or if the mains voltage is going to be running a little bit low, we could tap it on 110 0 from brown, white. Blue and brown are going to give us 0 and roughly 17, maybe 18 volts. And you might say, now hold on a minute, Aaron, I thought you were going to go for 24 volts DC. Well, in fact we are, because this is an AC output and we need to rectify it. We will do that using a device like this. This is a full wave bridge rectifier. So sketching this up, not including fuses and switching, we're going to have line and neutral coming in just like we were showing before. But right here, we are going to have our transformer, and we're just going to leave that 110 volt tap floating. It's not going to do anything. So we're going to have 120 volt AC in, and then on the output, we're going to have 17 VAC out. What we are then going to do is run it through this full wave bridge rectifier, which has two AC terminals and then a DC positive and a DC negative out. What are those, you ask? Glad you asked. Well, let's take a look. A full wave bridge rectifier is the most complicated arrangement of diodes that also gives you the best possible filtering of an AC signal. It looks roughly like this in schematic form. So here's our AC inputs, also shown on the bridge rectifier as this. You can also tell them apart on a standard rectifier because one side or corner will be notched. That corner is always the positive. The opposite corner is the negative, the other two are the AC. This one here also happens to be GBPC 3504. I believe that means it's rated for 400 volts and 35 amps, at least in theory. We won't be using anywhere near that much, but what we will be doing is connecting it like this. So this here is going to be our positive, and then face diodes pointing away from the terminal are going to be negative. So this here will be our positive output, and this here will be our negative output. We've got 4 diodes packaged in here, and what they are doing is they are rectifying both halves of the AC waveform. So when this side is pushing and this side is pulling, what happens? Well, we push through this diode and we pull through this one, positive and negative. When the waveform reverses, we are now pushing through this side and pulling on this side, and we push through this diode again to positive, and we pull again from negative. So what happens is we have our incoming AC waveform that looks like this. If you were to graph it on a, like an oscilloscope or whatever, let's just give 2 full cycles. Still looks like that over here, just at a lower voltage, so the peaks are lower. But when we get on the output side of our bridge rectifier, what's happened is we've done this. So our AC waveform is now hopping between 0 and some maximum positive value. The simplest form of a rectifier that you could do is just a single diode on one side. And if you're really feeling creative that day, you could install 2 individual diodes and just do that. But either way, you've still only got a halfway rectifier, because when you're pushing and pulling, it conducts. When the waveform reverses and you're pulling and you're pushing, nothing happens. And so instead of getting this nice neat waveform of 4, you would only get half. That still works, but nothing's happening here, here, and here. And worse, you're probably getting some fairly nasty harmonics injected back into your power system, because on these waveforms you'll pull current, and on the negative you won't. And so that causes a lot of jostling of the signal back upstream. This is the best possible configuration you can use, and so we're going to do it. And conveniently, because it's the best possible configuration, you can buy purpose-built devices that do it for you. One problem though. Let's zoom in on this. We have these halves of a waveform that look something like this. We've got to figure out what to do with that. Well, that's where these big fat capacitors come in. These are energy storage devices. These particular ones happen to be rated 50 volt at 4700 microfarads. I could probably get away with just one, but if you've got 2, why not? So what happens is once you smooth this output with some kind of capacitor, you still have positive and negative, but now you've got a device that is attempting to charge up and store energy on each pulse, and then it will discharge into the load between pulses, and so that comes down like this. The resulting actual current waveform is right here. Current and voltage waveform, I should say, are now a function of this. That's not perfect, but it's way better than what was going on before, where we were hop, 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 hop. This distance here is now your ripple voltage, as well as a ripple current that corresponds to this voltage changing across the load. So you do need to be careful to spec your capacitors so that the ripple current doesn't cause them to overheat and burn out, but I just know by experience that if I've got 4700 microfarads at 50 volts and I want to pull about 4 amps across that, it's probably going to be okay. And if I double those up, now I've got 9400, And that's more than enough. I mean, once you get to 10,000 microfarads, and those are the kinds of capacitors that you normally see installed in old school stereo systems before all of them started coming with switching power supplies. There's one more thing we need to be aware of, however. On an AC waveform, the maximum peak-to-peak voltage is not your RMS voltage, or mean square. So when I talk about 120 volts AC, 120 volts coming in is somewhere right around in here. The peak of the waveform actually goes higher by the square root of 2. So when you rectify DC and you're operating right here at the top with just this little ripple voltage on top, if I'm getting 17 to 18 volts AC out here, my DC is going to be that same 17 or 18 volts AC multiplied by the square root of 2. Okay, so going back to the calculator, let's just say it's 17. I take 17 times the square root of 2, which happens to be 1.414, 24 volts. So now, with the capacitors here, I've got 24 volts DC. I don't know exactly what this transformer's power rating is. I do know that the UPS it came from was 600 VA, somewhere in that range. So for sure this is going to be at least 150, if not more. And I need 133, so I've got my transformer, and this bridge rectifier should be more than rated for what we need. And I've got my two capacitors, which I can wire in parallel in order to get almost 10,000 microfarads of filtration on the output of that. This will give me a fairly nice, stable DC power supply to go into here. But wait, there's more. I can't just bring 120 volts from the mains outlet into a box. I've either got to bring a power cord through and use a grommet, or I can use an IEC inlet like this one. And this particular one happens to have a filter built in as well, which helps reduce EMI injection back into the mains. You can generally buy these all day long off of eBay, industrial surplus, wherever. However, I also need either a circuit breaker or a fuse. Here's a couple different options. This one's a fuse holder, AGC4. This is a 4 amp fast blow that I put in there. So this is one way of monitoring your incoming power. Another way, which is basically a fuse replacement, is this little panel mount circuit breaker designed to go into a similar size mounting position. This is rated 3 amps, also another good option. And if I want to switch my output, I can do that using a switch type circuit breaker rated for 4 amp full load, 6 amp trip, 32 volts DC, 250 volts AC at 50 to 60 hertz. JB Saunders Company, there's a name I haven't heard in a while. They used to operate in Boulder but closed years ago. Alright, so you've got to come in, you've got to fuse your incoming power somehow, then you can take it through your transformer, or you can take it through a power switch first. I'll have some kind of AC power switch that I bring this through before it goes out again. So that'll be installed in the front panel, switch it on, then everything lights up. So the DC output of this will come into this, and then I have to decide what to do with how to get to the output. And I think I'll use some banana terminals. You can buy simple panel mount ones, but I happen to have this little block of 4 from some old stereo I disassembled years ago. It had an unrepairable defect. So I'll probably mount these on the front panel instead. Another problem, however, is that once you start installing equipment like this, capacitors, whatever, you've got to mount them somehow. So I've got a little piece of circuit board, and I've got some standoffs here. I also have some other things going on here. One of them is this little mini buck converter. This thing is tiny, smaller than a postage stamp. But what it'll do is taps off the 24 volt, but is only outputting 12 volt DC, I think, to drive this miniature fan that I happen to have lying around. This fan should install somewhere near or over this heatsink and provide decent cooling so I can run this at full output. As you can see, this little guy for $17 is incredibly useful, and if I want to just connect it to, say, a laptop power supply and get an output from it, great. If I want to make a full self-contained power supply, however, there's going to be a fair number of other components I need to at least think about. Finally, my box. These cases are available all over eBay. Let's take a quick look at why they're relatively cheap. And there we go. That's why they're cheap. This thing here, it's fairly thin aluminum, so there's that. But the other issue you need to watch out for on this particular style of case is that most of the support is actually obtained through these plastic trim rings. So that's fine for a small instrumentation case, but it's nowhere near the quality of an all aluminum case where there's actually pieces folded over. If you have goals of having something look a little bit higher end, this plastic is not going to do the trick. It looks very cheap. It has molding warpage on it and whatever else, but for this project, more than enough. Now, why did I pick one that happens to look as big as all this? This one happens to be 9 and 5/8-ish by 4 1/4 by 7 1/2-ish. Well, mainly I need to be able to fit this giant transformer in there. So if you do a transformer based unit, you can see it'll go, and there's some clearance in there. This piece here and some of this other miscellany I'm going to put in there, it is going to take up some space, and it isn't going to completely fill this box, but I need to pick the minimum dimension available that would accommodate my largest power supply component, and that's usually how you're going to have to plan your project also. One way to buy gifts for the man who has everything is to discover cool toys on eBay before he does. I actually bought 2 of these power supply modules and gave one to my dad for Christmas, and he promptly turned his into a project long before I did, partly because he followed the KISS principle. Keep it simple, stupid. The power cord does not use an IEC inlet, it simply wires directly into the chassis with a cord grommet. There's a fuse on the back side, power switch on the front side. The only nod to complexity is a power indicator light, so if the light's on and the module's not, you know you've got power but the module's got a problem. Otherwise, it uses a simple 50 VA transformer and a capacitor and bridge rectifier that are quite a bit smaller than what we're going for here. If you're just testing small hardware, here's a way to do it a little bit smaller, a little bit cheaper, and quite a bit faster. Hey everyone, thanks for joining us. That was part 1. Part 2 is coming up next time. We do have to still build this power supply, and of course there's hours and hours of footage for that. We're just going to give you the highlights. There's a lot of things that we have to do to make this work, and hopefully you might get some ideas for your project. See you again next time, which should be shortly. Ad hits. Has anyone seen my phone?